Okay, welcome to our demonstration. So, did you ever wonder where the rainbow in the sky came from? Did someone tell you that a leprechaun made it and put a pot of gold at the end? Well, sorry to tell you this, they're wrong. Natural rainbows are the product of lots of refraction and reflection from the sun's rays into rain. But to really understand this in detail, we will be conducting an experiment that mimics how rainbows form. This experiment was first introduced by Sir Isaac Newton in the late 1660s. He wanted to investigate white light and the process of how it occurs. And he found that white light is in fact not white. Rather, it is a combination of all the primary and secondary colours which make up the visible spectrum.
The materials used for this experiment are a power source, a light source, some blank pieces of paper, a triangular prism, a Plato convex.
So the safety precautions for this experiment include being cautious of the pointy edges of the glass prisms. It includes ensuring that our power source is not too high of a voltage because it might overheat the light source, and making sure that we're not pointing the light in each other's eyes, just to be extra cautious. Okay, so now our white light is traveling through the medium, the triangular prism, and is refracting within the medium and causing a dispersion of the different rays of light. So each color, as you can see, I don't know if you can tell in the video, but there is a rainbow. This rainbow, all the colors demonstrate a single ray of light.
And wavelength.
And yeah, so now what we'll do is we'll get the other lens and we'll show you how it looks in a bigger way.
The reason why we've added a Plano convex prism is to enlarge the rainbow for you to see better.
So as you can see, the dispersion of the different rays of light is in the form of a visible spectrum. Now we will explain the key physics principles behind the demonstration we've just shown you. Salika, would you like to explain?
White light is a combination of red, orange, yellow, green, blue, and indigo and violet. See, when white light hits a prism, the white light is refracted, it's bent, because a part of the white light, when it enters a new medium, it bends because the speed is changed. And so each color and the separation occurs due to each color having a different wavelength.
An individual own wavelength, yeah.
Each color has a different speed, and the colors separate due to different wavelengths. So red is first in a rainbow because red has the longest wavelength. The length of the wavelength determines the time taken to pass through the glass. So red is the quickest and violet is the shortest. This is due to red having the longest and violet having the shortest wavelength. So red wavelengths don't interact with electrons as much as violet wavelengths because violet is like that and red is like...
The frequency is very small and short, whereas the frequency of the orange colours and yellow colours is a longer wavelength.
Therefore, red is faster than violet. The length of the wavelength determines the time taken to pass through the glass, so red being the quickest and violet being the shortest.
So as humans, we only see part of the electromagnetic spectrum, and that's the visible spectrum, which is the rainbow, what we're talking about today. To kind of relate that now to life sciences and physics of the life sciences, we're going to use the example of like an apple. So what happens is white light passes onto the apple. The apple absorbs every color of the white light except the color that it is. So if it's a red apple, the red wavelength will then reflect onto our eye. Our retina and our cones then receive this, and that's how we see and perceive color. Now to then relate that to what we began with, rainbows. So how it goes down, now using this as an example, is that the sun has the light, it produces the rays, the radiation of light. When it rains, the water droplets then act as a medium which the light refracts off, producing the colors that we just mimicked right here today.